Alrighty, let's go over the second lesson of week 12, significance test. I figured out why my videos weren't saving. Looks like I used up all the memory space on my MacBook. I was thinking I was erasing them, like deleting them, like putting them in this trash, but they were saving somewhere else, so I just didn't have enough space to save all these videos that I created. So they were keep getting lost, so I got frustrated. But I did clean some of the spaces out, so I should be able to save these. So I'm gonna go ahead and start 9.2. This took me about an hour last time I recorded it. Let me go ahead and open this up. This is This is the longest. This is the longest one in chapter 9. Oh, hello, somebody's in here. See, I wonder if I comment or say, can I chat with this person? Probably I should. He's probably here to just study. All right, let me go over these 9.2 significance test about proportions in this video. 9.3 and 9.4 make it a little bit quicker. It says, hi, I recorded this lesson video about 55 minutes long and my recorder crashed on me. It didn't crash. It was actually, the recorder just turned off because I didn't have enough space to save that 55-minute video. So, in the weekend I got so frustrated, so I stopped. I couldn't fix it. But now I fixed my technology issue. I am back recording our lesson. So remember, this week, I apologize for the delay in uploading this week's lesson. So I did change the homework due date. It's usually due on Thursday, but we will have until Sunday to finish this week's homework because I was late on uploading these lessons. But we're going to have it all today. Yep, I'll have everything ready for you today. All right. So let's talk about significance test about proportions in this video. Proportions. And 9.3, we're going to do the significance test about means. Okay? Kind of doing the significance test in 9.2 and 9.3. And in in 9.4, we're going to talk about errors. Okay? So step 1, we're checking some assumptions. And for proportions, make sure the variable that you're working with is categorical. For categorical variables, the parameter of interest are the population proportions in the categories, okay? So what percent of the people like apple? What percent of the people voted for this guy or that guy? Something like that. The variable must be categorical. And the second one, the data are obtained using randomization. Now, sometimes a good problem will say, the data was collected randomly, we did a random experiment, or this was a random sample. If it doesn't say it, I guess we're going to have to assume, we're going to have to make an assumption that this data is obtained using randomization. Otherwise, we wouldn't be able to make an inference about the bigger population. Okay? All right, number 3, the sample size must be sufficiently large, and we can look at the n and tell that. Now, how large do you remember? In section 7.2, we talked about sampling distribution of sample proportion p hat is going to be approximately normal if the number of success and the number of failures are both greater than or equal to 15, right? The number was 15. N times p, or n times 1 minus p, or n times q, must be greater than 15 in order for us to assume or use normal distribution for sampling distribution of sample proportion. So these are the 3 things that we need to check. Are the variables categorical? Check. Data obtained randomly. If they didn't say it, well, we're going to just assume that they did the right thing and we're going to go on. Sample size must be large enough so that we can use z-test statistics. So after that step, well, let me go ahead and remind you. About 7.1, recall that in section 7.1 introduced the sampling distribution of sample proportion. The mean was easy to remember, right? Mean was just the same thing as population proportion P, but then the standard deviation had a slightly bigger formula, which was square root of P times 1 minus P divided by N. Not only that you used this formula in 7.1, you guys used this last week and the week before when you were constructing the confidence interval and different things. So you still remember this is the one for standard deviation of sampling distribution of sample proportion, and it's well approximated by the normal distribution with bigger sample size. And the sample size had to be n times p had to be greater than or equal to 15, and n times 1 minus p, the number of failures, had to be also greater than or equal to 15. So if these numbers are not greater than or equal to 15, then we can't really do the significance test using the normal distribution. So I will make sure to give you all the problem that meets all these three assumptions, okay? Okay, and then we're going to do the significance test about proportions. Now, after checking those things, let's go ahead and write hypothesis, okay? How many hypotheses do we need to write per significance test? We need 2, right? In the first video, we went over 2 types of hypothesis. We need the null hypothesis and also the alternative hypothesis. Now, let's take a look at the null hypothesis of a test about proportion, the form of it. Now, remember the symbol H naught. H with a little circle, or with a little O or 0, or sometimes people call it H0. The null hypothesis will always have an equal sign. It will go P equals and some number P naught, and that P naught is just going to be a proportion. P naught is a particular proportion value between 0 and 1. And how do you figure out what number that is? We're just going to have to read the problem. If they say, oh, we think 40% of students are in favor of teaching math, blah, 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 then 40% will be that P naught. 0.40 will be the P naught. So P naught will be replaced by a number. It's going to be between 0 and 1. And we're going to make sure to write the null hypothesis and the alternative hypothesis using little p. And we'll talk about the importance of using the population parameter symbol for these hypotheses. We are never going to call the null hypothesis or alternative hypothesis with p hat. Not going to use sample proportion, always going to use population proportion. All right, p naught is read as p0 or p naught. I just read it as p naught. And it's the hypothesized value of the population proportion under the null hypothesis. That's what they claim, so we're going to test it, okay? That's what they will claim in a problem. So that P naught, stick that as your null hypothesis. And what we're going to do is we're going to write the alternative hypothesis and go on and do a significance test. All right, so what's the second type of hypothesis? The alternative hypothesis. So this is what we're doing in a significance test. Listen. We get 2 sets of hypotheses. We're going to do something to reject the null. So if the null hypothesis is false, then we're going to have to believe the alternative. That's what we're going to try to do. So we're going to have the second hypothesis, the alternative hypothesis, refer to alternative parameter value from the number in the null hypothesis. And remember from section 9.1, we talked about how these are going to be a range of values. So either HA, and look at the notation, the little a for alternative. HA is either P is greater than P naught, or it can be P is less than P naught. Notice these are range though, right? All the numbers that are greater than P naught or all the numbers that are less than P naught. Or it can be in the form of simply, hey, P is just not equal to that number. It can be anything else, but it's not going to be that number. So take a look at the difference here though. The first two are the first one is going to the right side of the P naught, is greater than. The second one is going to the left side of P naught, is less than. What about the last one? It's really going both sides. It's saying it's not equal to P naught. It's like saying, oh, it's just not 0.50. I don't know what it is, but it's not 0.50. Well, then the alternative is considering anything greater than 0.50 and anything less than 0.50. So the first two are called one-sided alternative hypothesis because it has values falling only on one side of the null hypothesis. It's either greater or less than, okay? And we can tell them by reading the problem carefully. Okay, if there's a reason for us to believe that the alternative is actually greater than what they claim, we're going to go with the first one. Or if it's less than what they claim, we're going to go with the second one. But very often in practice, we're not going to know that. So it's very common to do just this two-sided test. The last one, P does not equal to P naught, is called a two-sided alternative hypothesis, as it includes both below and above the value TP naught. Now, I happen to pick more examples that are one-sided in this example, in this lesson. But in practice, it's more common to do two-sided alternative hypothesis, as we can connect the result of a two-sided hypothesis test with the construction. What's it called? Confidence interval. And we'll take a look at that together, I think, toward the end, maybe like slide number 30 somewhere. We have it. Alrighty. So remember writing two hypotheses. Well, this is just a picture of how, if you're just considering, hey, P must be bigger than 1/3, then you're just looking at all the numbers that are greater than 1/3 but smaller than 1. if you're considering, hey, P is just not 1/3, then you gotta consider both the right side and the left side. And we'll do, I think we're gonna do a bunch of one-sided tests, but two-sided tests, we'll also talk about that. Now, 3 basic facts when specifying hypothesis though. Null hypothesis has an equal sign, right? Such as H naught is P equals 0.50, but the alternative hypothesis does not. It's not going to have the equal piece in it. It's going to have either greater, less than, or not equal to. So the null hypothesis, set it up so that it has an equal sign, okay? You shouldn't pick HA based on looking at the data. Well, if one observation kind of tells you, like, remember we kind of talked about the pizza example, and pizza is really the average mean time, average delivery time, so it's not proportion, but yeah, that example about proportion of students who are successful. If the university claims that 70% of students are successful, and if I see like more than half of my friends dropping out of this class, then I kind of have a belief to believe that the proportion of students who are being successful is maybe less than 70%. So unless you have a good reason, well, you're going to pick an alternative hypothesis before looking at the data. And once you set your hypothesis, and if you really didn't have any reason to make it one-sided, just go with two-sided. The one that does not equal to symbol. But, once you do your probability and test statistics and everything, you shouldn't go back and change your alternative hypothesis just because you want to reject the null. Okay, so pick your hypothesis in the beginning of the study. Hypotheses always refer to population parameter, not sample statistics. Okay, so this is why I said never use p hat or x bar. X bar stands for sample mean, and p hat stands for sample proportion. We don't really, if we want to find the sample mean and sample proportion, we can just find it in a sample, right? But what we are trying to do is we're trying to work with the bigger picture here, guys. We're trying to find the proportion or the mean for the bigger population. So it's a very common mistake when people write these hypotheses, they accidentally use like p hat or x bar, but that's not what we're trying to estimate, right? We're trying to estimate the p, the little p for population proportion, and this little, Greek symbol mu for mean, population mean. So do not ever use p hat or x bar when you're writing hypothesis, okay? Some basic facts, very important facts about hypothesis. All right, let's write some hypotheses, okay? Now that's going to be the very important step where we actually set up this significance test. So here's Sue. Sue hypothesized that more than half of her students wait until Thursday to start on their weekly math stat lab homework. What are her hypotheses? Now, she said she thinks more than half of her students kind of wait until Thursday. So half is what? 0.50, right? 50%. So remember, the null must have an equal sign. So the null hypothesis, H naught, is going to be little p, population proportion equals 0.50. Okay, that's going to be her null hypothesis. But what she wants to do, what I want to do in this study is I want to reject it, because guess what I believe? I think more than half of my students are waiting. So more than half. What I believe is p is actually greater than. So my alternative, HA, is going to be little p is greater than 0.50. Notice how in the context, like I said, more than half. She hypothesized that more than half. That's why I'm making this one-sided test. I'm making it p is greater than 0.50. But if she simply thinks the proportion is not really 50, then I could have made this not equal to 50. But as you can see, just gotta read it very carefully to decide the alternative hypothesis. And do write it with symbols and everything for me, okay? Let's look at number 2. Luna wondered if more than 10% of students enrolled in an introductory statistics class dropped before the second exam. Why is she wondering that? She's wondering if more than them are, so 10%, okay? She noticed that 2 out of 12 of her students. Now let's see why she thinks more than 10% are dropping out. What is 2 divided by 12, guys? 2 divided by 12 is 0.16. So about 17% of her friends in the class dropped before the second exam. Now, somebody probably told her about 10% drop before the second exam. So that 10% is what she's not really believing. She's thinking it's more than 10% because 17% of her friends dropped. Now, here's an assumption that I need to make, though. Assuming that she picks random friends, it's kind of weird, right? Assuming that her friends are randomly sampled, based on her sample, she's going to perform a hypothesis test. Is the hypothesis test one-tail or two-tail test? Let's think about this. Now, first of all, what's the null hypothesis is going to be that little p equals 0.10%, right? But what is she wondering? She's wondering if more than 10% are enrolled. So what she's thinking, based on her single observation of 2 out of 12, which is about 16%, she thinks the actual population proportion is greater than 10. So if she's using that greater than symbol or less than symbol in her alternative hypothesis, this is going to be a one-tail test, since the alternative hypothesis states that the parameter is actually greater than the hypothesized value. And that the hypothesized value is 0.10. Somebody, I guess the school probably told her that about 10% dropped before the second exam. But what she noticed on her single observation from her group of friends is that 16% dropped. So she's assuming that P is actually greater than 0.10. So by reading it, you should be able to tell if a test is going to be one-tailed or two-tailed, okay? One-sided or two-sided, same wording. All right, now why am I showing you this, right? Because the third example that I'm about to go over with you is talking about, what was it called? Astrological signs, symbols. I found that I am a Pisces. What is yours? Okay, but did you know that there are 12 astrological symbols out there? So there are 12. So if I randomly guess, what is Miss Vera's astrological symbol? I think she's a Libra. I don't know. I have a 1 out of 12 chance of getting it right if I'm randomly guessing, right? If I don't know anything about anything, then if I randomly pick somebody's astrological symbol, it's going to be just 1 out of 12. So here is my third example. A person who claims to be psychic says that the probability P that he can correctly predict the outcome of the astrological sign of a person in another room is greater than 1 out of 12. So he's saying he can do better than the random guessing. The value that applies with random guessing, and you understand why that 12 is there, right? Because there are 12 total astrological symbols, signs out there. If we want to test this claim, we could use the data from an experiment in which he predicts the outcomes for n trials. State hypothesis for a significance test, letting the alternative hypothesis reflect the psychic's claim. So we got the number, right? The number, the hypothesized value, is going to be P equals 1 out of 12, right? P equals 1 out of 12. But what is the psychic claiming? He says he can do better than that. So the alternative claim is going to be P is greater than 1 out of 12. So this is going to be another one-sided test because this person is just saying he can do better than that. But I don't know how, but I just happen to find all these great one-sided examples for you. But like I've been keep saying that in practice, it's more common to go with two-sided test, the one that has a not equal to symbol for the alternative. Okay? All right. Deciding between one-sided and a two-sided test. So how do you decide it? In deciding between one-sided and two-sided alternative hypothesis in a particular exercise or in practice, consider the context of the real problem. We had a very good reason to believe that our previous 3 examples are going to be all one-sided, right? So read the problem very carefully. Go with the context of the problem. In most research articles, though, significance tests use two-sided p-value, okay? And there's a reason. Because remember, confidence intervals are two-sided, right? Because confidence interval, we had the 95% in the middle, and we had some to the right and some to the left. And we're going to connect that together, I think in maybe the very next slide. You should use two-sided tests unless you have a well-justified reason for a one-sided test. So unless the context of the real-world problem is telling you to go with one-sided, you can always go with just two-sided test, okay? Because that's more common. So let's try to connect, because remember they said, hey, something about the confidence interval and two-sided test. So let's connect that right now in this slide. connection between confidence intervals and significance test. Now, results of 99% confidence intervals are consistent with results of two-sided tests with significance level alpha equals 0.01. Now, what are they talking about? Now, I need to tell you what this alpha, this significant level is. But what is 0.01 in percent? That's 1%, right? Now, look, guys, confidence interval has 99% in the middle, right? If it has 99% in the middle, to the right and to the left, on those two sides, how much do we have left? 1%. That's what they are saying. So if it's not in these confidence interval, it's going to be in these margins. 0.5% to the left, 0.5% to the right. So, how do we tell? Well, they're going to add up to 100%. So next number, like 95% confidence interval are going to have a consistent result as the two-sided test with significance level alpha equals 0.05. What is 0.05? That is 5%, right? So having 95% in the middle for the confidence interval, and we're going to have the margin 5% in both the left and the right side. Well, together they have 5%. So if we fail to reject that it's not in those regions, it must be in that confidence interval. But it probably will make more sense if you do a significance test together first. But I did find a problem like this on your homework, so just wanted to go over them with you together. If you add 95 plus 5%, they add up to whole 100%, right? So the last one, what if it is 90% confidence interval? The results are going to be consistent of two-sided test with significance level of 0.10, and 0.10 is 10%, so 90% in the middle is going to be the confidence interval, and the outside region to the left and to the right, those are going to be the rejection region. We call them rejection region. So, because if a two-sided test with this significant level does not reject the null hypothesis, then the confidence interval will contain that value in the null hypothesis. So it's either in that rejection region or in the confidence interval region where they're going to say that's kind of common to have. So in a picture, see, I found this picture online. I kind of wanted to copy this little guy on the left and paste him over here too, because I wanted to make it two-sided. Now remember, there's this confidence interval in the middle. If you're in this region, you're not rejected. You are common. You are, with the other 95% or 99%, we're confident that that's the true population proportion. But let's say you're in this rejection region. You are that extreme, right? Either this side, or it could be also on the other side. So if it's not in this region, well, it's going to be in that confidence interval. Okay? That's what this connection between confidence interval and significant tests are talking about somewhat. But then take a look. 99% confidence interval will have the same result as the two-sided test with significance alpha 0.01. I think this slide will be helpful in answering one of your homework problem. All right, so we did two things. We did only two things so far. Assumption checks, and then the second one, hypothesis writing. And then number 3, we're going to do something called test statistic. And this is the mathy part. This is a math formula. Why did we have to check the sample size? Because when the sample size was big, the number of success and the number of failures were at least 15, then we get to use normal distribution, right? For population proportion, the significance test will use something called z-test statistics, and it's nothing more than z-score, really. So when I ask you to find test statistics for significance test for population proportion, you really just find the z-score. And the formula goes like this. And looks kind of crazy, but you know every piece of it. This is what you're doing. You're subtracting your p-hat, your sample proportion, minus the value under the h-naught, okay? This is the hypothesized proportion. And you're going to divide this by, it says SE-naught. Well, that's the standard error when the null hypothesis is true. And remember that formula, and it's kind of bad because in the previous section, chapter, we did have p-hat in the square root, but what we're doing is we're assuming that the null hypothesis is true. So do use p-naught in here. If you look at this formula carefully, p-naught is used 1, 2, 3 places, and p-hat is only used once on the numerator. There are a couple problems where you will have to find z-test statistics by hand, and if you have to, this is the formula you're going to use. And many other times when you're doing a significance test, you can just use your StatCrunch, and then they will find everything for you. But I found some homework problem that looks like this. They will not let you use StatCrunch. They will actually ask you to use this formula to find z-test statistics. So I can't remember which one this is, which number it was, but I think I got this from your homework. For a test of H0, P equals 0.50, the sample proportion is 0.39 based on a sample size of 81. Now, in that first sentence, they gave us 3 numbers, okay? And they want you to use this information to find the test statistic z. Now, remember, test statistic formula is just a formula. We gotta plug in everything in and follow the rule, and we'll find the z-test statistic. So let's label everything. What's P0? P0 is the number they used in the null hypothesis. So P0 is 0.50. Now, sample proportion is P hat. So P hat is 0.39, and the sample size of 81, n equals 81. So label these 3 things for me. P hat equals 0.39, P0 is 0.50, and n is 81. And if you look at that formula, that's the formula, right? We're ready to plug in every number that we have here. Z equals, the numerator will be 0.39 minus 0.50, but then the denominator, we just have to plug in 0.50 everywhere we see P0. And then remember, n is 81. No reason to do this, numerator, denominator. Just type this into your scientific calculator. What I did was I went to Desmo scientific calculator and I just typed this in. What you will get is a z-test statistic of negative 1.98. Now the thing is, you work with normal distribution for like the last 3 months. You know what this number is. This is about negative 1.98 standard deviation below the mean in a standard normal, right? So how unusual is that? How unusual is that? And that question can be answered by something called p-value. But this is how you find test statistic. If a question is asking you to find test statistic, you really need sample proportion, your P0, and then your sample size, and you'll be able to just plug it into your z-score formula, okay? And remember, the z-score formula, you divide by the standard deviation, but we were dividing this by the standard deviation. Well, this is the standard deviation formula for sample proportion, right? So these kind of monstrous formulas are kind of coming all together. We've been learning one thing at a time, but now we're kind of putting everything together. Now, so let's talk about how unusual it is to see that number, negative 1.98, and that is what p-value is. Does your test statistic give much evidence against H0 and in support of HA? So what we're going to say is, how unusual is it to see that? It's so unusual that it will let us reject the H0 and go on with the alternative. That's what we want. So p-value summarizes the evidence. It describes how unusual the observed data would be if H0 were true. So the whole process of significance test, we are assuming that H0 is true and deciding how unusual, how unlikely is for such sample proportion to happen if the null hypothesis is true. So let's find that probability. And how do we find that probability? Well, it's a standard normal, right? So use standard normal distribution to find the probability. So take a look. For a test of H0 equals P equals 0.50, now we're just given P0, so label this as P0. Z test statistic equals 2.57. Now imagine that. Picture that in your head. Where is that number on this standard normal distribution? 2.57. It's 2.57 standard deviation above the mean of 0. It's to the right side. And remember, our standard normal really goes from like negative 3 to 3. This is pretty close to 3. This is very, very big in that distribution, right? Find the p-value for HA, that p is greater than 0.50. When they say they want the p-value for the alternative that p is greater than 0.50, it's greater than, right? What they are asking you is the right tail probability, because if it's greater than, it's going to go to the right, right? So if it's greater than, then we're going to find the right tail probability above z of 2.57. Now, if it was flipped, if it was p is less than, then we would have found the left tail probability, but then they will probably have the z-score to be a negative value. But let's go ahead and find it. Simply, p-value is just a probability, guys. So go to calculators, go to normal, okay? Because we have a z-score that we want to find the probability of. Type in this. Remember, standard normal has a mean of 0 and standard deviation of 1. Now what we want is, we want the area that has, we want the probability that has, probability of, yeah, really the area is the right word. Area to the right side of 2.57, because we're looking for the right tail probability, right? So if you type that much and hit compute, ta-da, they're going to give you this. Take a look at that probability. P-value is 0.005. P-value is 0.005. That is a small probability of such thing happening. So what we just got is this. It is very unusual for that z-test statistic to happen if the null is true. This is a strong evidence for us to reject the null, because this is so unusual. We're not going to believe the null. Okay, so we'll talk about that in one more slide, but let's do another p-value for statistics. Now remember, this one that we just did was one tail, right? This is just to the right side of it. This was when x is greater than 2.57. If the z-score was 2.57, the right tail has 0.005 to it. What if I ask you to do two tail? You see, then what we're going to do is we're going to also find the area to the left of negative 2.57, which is going to be exactly the same as 0.005, because look at this curve. This is perfectly symmetrical, right? So if they ask you to do a two-tail test, for test of h0, p equals 0.50, and the z-test statistic equals 2.57, they want you to find the p-value for ha, where p doesn't equal 0.50, does not equal to 0.50. This is a two-tail test, right? Because we have to look at both greater than or less than. P-value for HA, p doesn't equal to 50, is a two-tail probability above 2.57 or below negative 2.57, okay? So both tail, we need to look at them for these two-tail tests. So guess what we can do? We can just use the probability that we got on our previous slide and multiply that by 2. What are we using? We're using the fact that normal distribution is perfectly symmetric, okay? So if you do that, the p-value comes out to be twice as big as 0.005, which is 0.01, okay? Last one. Now, you probably won't see this very often because it's kind of silly to go left tail when your test statistic is positive number. You do the left tail when the test statistic is negative, but, well, we'll see it. For a test of h0, p equals 0.50, the z-test statistic equals 2.57. This is a number on the right side, right? They want you to find p-value for ha, where p is less than 0.50. So, if it's less than 0.50, you know what they want. They want left tail probability below 2.57. It would have made more sense if they ask you for below negative 2.57. Well, we have lots of numbers that are smaller than 2.57 on a standard normal distribution, right? Well, let's find it for them, but we're expecting something big. All right, go to calculators and normal, and take a look. That's what I typed in. Mean is still 0, standard deviation is 1. And find the left tail. It's not even called a tail. This is like the entire body. X is less than 2.57, and that p-value comes out to be what? 0.994. 995 rounded up. So, is it unusual to see something that is below 2.57 in a standard normal? Not at all. There's like a 99.5% it will happen that way. So, if you see something like this, you're not going to say this is unusual. You will fail to reject the null if this happens. So we should see which ones out of 1, 2, and 3 provide strong evidence against h0. I think on the PDF file, I typed in HA there. So if you can fix that for me, if it's not h0. The p-values are the evidence against h0. Okay? So, yes. P-values of example 1 and 2 are very small. Remember, the first one was 0.005 and then the other one was 0.01. These p-values give strong evidence against h0. These small p-values indicate that the null hypothesis is not plausible because it was very unlikely to get such small, a small probability if the null is true. So here's a good review of 9.1. If p-value is small, what do? You must reject the null. If p is small, you must reject the whole, okay? H naught, okay? You would say, oh, this significance test was successful when you get a small p-value, okay? But this is what I mean by you shouldn't just change your two-tailed test to a one-tailed test just because you want to cut your p-value down to half, okay? You can't do that. But let's talk about how to write conclusion based on that p-value. Now, significance level is a number such that we reject H naught if the p-value is less than or equal to that number. In practice, most common significance level is 0.05, so 5%. Now remember, the numbers that we got was 0.005 and 0.01. Those are both smaller than 0.05. If you get a number, p-value that's smaller than the typical significance level of 0.05, then we get to say, oh, we reject the null, okay? 5% is what we consider to be the standard, okay? Like if it's less than 5%, we're gonna say, oh, it's very unusual for such thing to happen. All right, when the data provides sufficient evidence to reject H naught and support HA, because once you reject the null hypothesis, you can go and believe the alternative. When the p-value is less than the significance level, the result of the test are called statistically significant. That's a big word, okay? If you want to say, oh, this result is statistically significant, you better show that your p-value came out to be smaller than your preset alpha level or your significance level, okay? If your p-value come out to be like 0.12, like 12%, then that's not going to be statistically significant. We want it to be smaller than 5%, okay? Alrighty, so why is it statistically significant? Imagine getting because the normal region will be like from this number to that number. But if you get a number that is in this pink region, you know something is off, right? That's kind of unusual. So if that happens, we're going to reject the null. That can't happen, right? That's so unusual. The null must be not true. Therefore, I must go and believe the alternative. That's how it goes in the hypothesis testing. All right. Oh, goodness. I got summary slide for you. I'm not going to go through all of them, but if you missed any blanks, this is going to be a great summary. It's talking about number 1, checking for assumptions, hypothesis, and how to find the test statistics. We went through each and every one of these. If it's greater than hypothesized P naught, then we're going to do a right tail probability. Less than, then it's going to be left tail. And for the two tail, you have to look at the right extreme and the left extreme, and they're equal. So you can just simply find the right tail or the left tail. You find the right tail if the test statistic comes out positive. You find the left tail if the test statistics comes out negative, okay? And then you can simply multiply them by 2 to find the two-tail probability p-value, okay? Conclusion was the important part. Smaller p-value gives stronger evidence against H naught. If a decision is needed, reject H naught if the p-value is less than or equal to the pre-selected significance level. And the important word, I guess, here is the pre-selected. You can't get a p-value of 0.06, like 6%, and decide, oh, I'm going to make my alpha level 10% so that I can reject it. No. If not sure, just set it to be 0.05, 5% significance level, and you cannot decide your significance level based on the p-value you get just because you want to reject that null. Okay, can't do that. Relate the conclusion to the context of the study, and we'll do one together. And this is actually from a homework. Did I number it? I don't think I numbered it, but you'll see this is about therapeutic touch, TT practitioner. Now, how long have I been going for? I've been going for 39 minutes. I may need a water break, but I think I can finish it. Hopefully this video is safe. If it doesn't, I'm gonna lose it, guys, because this is really 3rd time re-recording this. That's why I was so late uploading these lessons. I may just do a Zoom with you guys next week. All right, but let me see. Let me go back and go over this last example with you, and I will also show you how you can do this on StatCrunch, okay? Therapeutic touch, TT practitioners claim, listen very carefully, what are they claiming here? To perceive an energy field above a patient's skin. They can feel something. To test this claim, a TT practitioner was blindfolded and the researcher placed her hand over either the right or left hand of the practitioner. Let P denote the probability of a correct prediction by a TT practitioner. Now, listen, they're right hand and left hand. Random guessing, she has a 50% chance of getting it right, right? But if she is really what she claims to be, she can feel the energy field above the patient's skin, then she should do better than 50%, right? All right, let P denote the probability of a correct prediction by a TT practitioner. On experiments used, now let's see, 14 TT practitioners. So there are 14 people involved, hopefully randomly selected, right? Who had to predict the correct hand in each of 9 trials. So listen, 14 of them each did 9 trials. So how many trials? What's the sample size here? Do 14 times 9 for me. 129 trials we have. So they did, 14 people each did 9, so 126 is the sample size, okay? Sample size is not 14 here. Sample size is 126. So if they're really good, they should get more than half of their guesses right? Let's take a look. So parameter of interest and hypothesis to test. What does P stand for? What's the parameter of interest that we have here? P is the probability of correct guess, right? And what we think, I mean, if it's completely, bogus, if it's just, they don't know what they're doing, then the probability is actually going to be just 0.50. Right hand, left hand, 2 hands, so 2 options. So there's a 50% chance that this person will just randomly guess and get it right. But what they are claiming is that they can read the energy field, right? So if they can do all that, they can do better than 0.50. So that's why the alternative is one-sided, because they claim that they can do better. So P is greater than 0.50, and we're going to perform a one-sided significance test because the alternative is just P is greater than 0.50. Ready? Now, suppose 126 trials had 74 correct guesses. Now, you understand where they got that 126 from, right? Remember, there were 14 TT practitioners. Each of them did 9 trials. So 14 times 2, they all did together 120. Well, they did 126 trials altogether. And look, they had 74 correct guesses. I'm just going to do a quick p-hat here. What is 74 divided by 126? Well, that is 58%, 58.7%. That is higher than 50. If I did, I think I found it over there. If I did 74 divided by 126, you know what? The success rate for these TT practitioners are 58.73%, and that is higher than 0.50. The important question is this, though. Is it high enough to be considered statistically significant, though? You see what I mean? That's why we're going to do a significance test. Now, N is 126, because we did 126 trials. Now, what's this? What I just find? Z-mess. This is Z-test statistics. Using the p-hat, p-naught, and N that we just identified, we can find that the Z-test statistic is 1.96. So step 3 was calculating this test statistic, and that comes out to be 1.96. The test statistic is Z equals 1.96, which represent the number of standard errors that the estimate falls from the null hypothesis value. So it is 1.96 standard deviation above the mean of 0. So how likely is it going to be that good or even better? Let's see, report the p-value. So this is me finding the p-value using the same method that we did in a couple slides ago. I just went to normal calculator, type in that the mean is 0 and standard deviation is 1, right? And because, look at our null hypothesis, the alternative, P is greater than 0.50, we're looking at right tail probability. That's why I want to find, besides Z came out to be a positive number, I want to find the area to the right side of 1.96, and look at that number. The p-value came to be 0.025, and that's even rounded up, right? That's a very small p-value. Since the p-value is less than the significance level of 0.05, the common significance level, we're going to reject the null hypothesis. Guess what? There is evidence that TT is more effective than just random guessing, because we just rejected the null that TT is just completely random, but we just rejected that and we are going with the alternative. They're actually doing better. Okay? So the alternative, that's what we are believing this time with such small p-value, because it will be very, very unusual. Less than 3% chance of that happening, of 74 correct guesses out of 126. if TT is really completely random. Okay, so this is a very great news for TT practitioners. So what about the p-value for the two-sided alternative though, right? Now we're kind of worried because in order to get the two-sided alternative, guess what we have to do? We have to multiply this by 2, right? So if I multiply this 0.025 by 2, guess what? We're still getting 0.05. And that is less than or equal to the very common alpha level of 0.05. So this is a good success. Inference, let's talk about that. Sample size, wasn't it large enough? 126, and assuming these TT practitioners were randomly selected, we can apply this inference to all TT practitioners out there. So I should maybe find one because they're good. They know what they're doing. So that's how you would do a significance test to make a conclusion using statistics. We were able to tell, well, this number that they got, 74 out of 126 correct guesses. That is statistically significant for us to believe that TT practitioner, TT, is actually more effective than just random guessing. Okay? Now, we can do this on StatCrunch, this entire test on StatCrunch. So take a look, because I know you like it. Go to Stat, and go to Proportion Stats, and click on one sample with summary. You've been here before. You know where? You've been here before because you were doing your confidence interval on this very same calculator last week. Go here, and this time, well, enter these numbers in there. The number of successes were 74 correct guesses out of 126. Remember, in chapter 8, we did the confidence interval for P. Today, we're doing hypothesis test for P. Set the P naught, the hypothesized proportion to be 0.50, and the alternative, HA, is going to be P is greater than 0.50 because they are claiming they are better than random guessing. Compute it. Guess what they're going to give you? This is the output table. And this has the same z-test statistics. If you round that up, you will get 1.96. That's the number we got. And also the p-value, 0.025, and the same p-value we got by doing this by hand. So up to you. If you have a problem that will let you just type this in your StatCrunch calculator to do the significance test, that's fine, that's fine. But sometimes they will word it somehow so that you can't really use it and actually do the things by hand. But this example, I was able to do it on the StatCrunch calculator. And that is it for this section. Sorry, this was about like 47 minutes, and I think I talked very fast. But I will be back with 9.3 lesson, which is about 45 minutes, like 40 minutes-ish. But then 9.4 is going to be very short. I'm going to go ahead and delete this box because I just recorded this. I think, hopefully you guys are watching this because I am praying so hard. Please save. I'm going to go ahead and stop this video and see if it's saved on my computer this time, okay? I'll see you on 9.3 video soon.